Hi everybody, my name is Mathew Holderman and I'm going to be presenting on my senior design project for here at Xavier University. Now, I'm a member of a team, and the other two people in my team who sadly can't be here today are Frenette and Duncan Wilgress-Pipe. And Dr. Hyderabad is my advisor for this project. So what are we doing? We're taking essentially a standard bike and we're turning it into an electric bike that considers the cadence of the pedaler and regulates the output of the motor. Now we're also taking this bike and we're using the energy from the wheel spinning to run it back into the battery to hopefully extend the battery life. So the joke that I like to make is that we're taking a bike from Walmart and we're essentially making it to a Prius. So why? So bikes, they're good exercise, but when you go up a hill, you can really start to notice the limiting factor. They're a lot of hard work to bike up, and even with electric bikes, you can see this. The steeper the hill, the harder time it takes for the bike to get up. So we're hoping that with our electric bike, the cadence sensor will help alleviate some of this stress and make it more of a team effort between the electric bike and the actual user itself. Now, these electric bikes also do have a battery life, and we're hoping to extend this battery life with our axial flux alternator. So how? So essentially we're taking our bike, we have our electric hub motor, which is the electric bike with the motor. The adaptive cadence sensor is taking the cadence of the pedaler at the pedals themselves and feeding it back into what's called a PID controller to modify and output the output of the motor itself. And then the axial flux alternator, we're taking the spinning action of the bike wheel and we're using something called Faraday's law to create an electric current from that and feed it back into the battery. So this is the block diagram of the mechanical system for our bike. As you can see, I'll leave it for a second to look around and then I'll move on for a second. So at the hub of it is our PID controller. So what is PID? Essentially, PID is an acronym that stands for Proportional Integral Derivative. Now, this acronym stands for how the controller uses the movement to affect what it's outputting. And another way to look at this is past, present, and future. It uses the past outputs, the current outputs, and the future past inputs, current inputs, and future inputs to determine how it's going to operate, let's say, a motor. A great example of this is a elevator. If you ever notice in an elevator, it never stops abruptly and you shake. It always comes to a gentle stop, and you never truly get shaken in a well-functioning elevator. Now, they can be more complex than this, but this is an easier way of explaining it all. Now, the implementation of this PID controller. So the speed of the DC motor can be controlled using this controller, and our option that we're going to use is a PID controller. We're going to effectively create levels for the user, levels of power for the motor to output, and we'll have parameters that we'll have to discover, and we're currently in the process of discovering, that will fine-tune this software and this controller itself. At bottom is our transfer function for this controller. And, sorry. So the adaptive cadence sensor. This is going to track the revolutions per minute of the user pedaling. We're going to use a magnetic reed switch to track a revolution. And this is going to link with the PID controller to track the revolutions. Now we're going to alter the amount of power to our electric motor that the electric motor will exert on the drivetrain, which will be based off of the speed of the pedals themselves and will be pushed over by the user, will be pushed by the pedals being pushed by the user, sorry. The faster you are going to pedal, the less power the motor is actually going to output to the bike itself. And the PID controller will alter the amount the battery the motor receives, the amount of the battery the motor receives, which affects the power in its outputs. Now the axial flux alternator. This is the meat of the project. So for Faraday's law, if you have a magnet passing over a coil of wire, it's going to create a magnetic field, and magnets with alternating polarity, so north on top, north on bottom, you're going to create what's called an alternating current, which is AC power, which is essentially what runs through your wall outlets. And we're going to run this through a rectifying circuit, and we're going to create DC power, which is what stuff runs off. We're going to send it into the battery itself. Now we're gonna actually have two different discs of magnets with the coils in between, because as the bike is nothing's ever perfectly straight. So as it shifts left and right as the bike moves, it'll never be too far away from any of the magnets, thus not negatively affecting the output of power. And once these we're gonna call them flywheels. Once the flywheel plates are spinning, an electric current will be induced in the copper coil, hopefully. And this will run in series with a rectifying circuit that will be connected back to the bike's battery. That's what we were doing. And these are some of the calculations that we're going to be using with a display of our circuit that will run back into the battery. So with how the currents work, it'll be alternating back and forth. So no matter which way the current is moving, it will be directed into the right end of the battery, the correct end of the battery. So these are some preliminary calculations we're going to be using. So we're going to be using a lot of production elements in this bike along with buying a basic bike. So we're going to be using the wood shop in the physics department, and there's a CNC mill which we are currently using to CNC our flywheels, which will be holding the magnets. And we have to use a non-magnetic metal. I think we're using stainless steel right now. And we also have to use a lot of 3D printing. Now we're using that to hold the coils, and we're using production softwares like Fusion 360 to make our coil holders. Those will be attached straight to the bike itself, while the flywheel will be attached to the wheel, thus having the coil holders not move while the flywheels will move with the bike. Now we are going to use a couple different types of 3D print filament. We're not just going to use basic PLA as it's not very professional. A couple of the ones that we're going to be using are PC ABS, which is very durable and heat resistant. We're using ASA, which is UV and weather resistant, which will be used for the outside mechanics, thus protecting everything from the elements. And we might be using an SR30 filament, which is a support filament that you can use in tandem with other 3D print filaments. And we were looking at stainless steel, however, we believe it's going to be too costly and maybe too heavy, so we're ruling it out as just not an option. And then this is the parts that we are using for the electric bike part. Now, any great team has roles, but these roles are fluid based off what we need. So our roles are more of what everyone's in charge of. However, with the needs of the project, we are alternating, ebb and flowing like the tide with what we currently need. So Duncan, Wilgress-Pipe is our project manager. He's the one with the most contact with suppliers and Dr. Rod. He's also our design specialist and he's doing all of the cadence calculations. Anna Frenette, she's our mechanical engineer is what we're going to call her. She's also doing a lot of the electrodynamic calculation for the axial flux alternator. And I'm the fabricator, essentially. And I'm also doing the primary software engineer. So I'm in charge of the 3D printing and the programming of our various sensors and PID controller, along with physical aspects of the project. So we're using a lot of courses through our Xavier education for this. So our axial flux alternator using classes like electromagnetism and circuit analysis. The PID controller is using a multitude of classes, microprocessors, control systems, signals and systems, along with others. And then the sensors we're using, which are attaching onto the bike as performance sensors, also using similar classes to the PID controller, along with the electric motor. Yeah, we're using all the classes that we've learned in our Xavier education to make this bike a reality. So, thank you.